Good afternoon, welcome back from lunch. I'm Ulrike Tillmann, I'm a long-standing member of this department here at the moment, seconded to the Isaac Newton Institute. It's a real pleasure to introduce Burt Totaro to give this lecture on the Hodge Conjecture. The Hodge Conjecture is all about the interaction in some sense of algebraic topology and algebraic geometry, and I think Burt is the ideal choice to give this lecture. He has really been working in this intersection for all of his life, as far as I can see, and most of his work has been actually, inspired by the Hodge Conjecture, and in particular, his results are also very much on this intersection. One result that is particularly highly cited and certainly close to my own heart is the results that he proved a long time ago about the configuration spaces of the varieties when their homology is actually determined by the homology of the variety. And that's very much an interplay between topology and algebraic geometry. So Burt was a young student. At the age of 13, he went already to Princeton University, later then to Berkeley, and studied with Kobayashi, and is now the professor at UCLA. He's quite well known to the British, UK mathematical community because he also spent 13 years as a Londonian professor for astronomy and geometry in Cambridge. Just a few of his accolades, many of them. He was one of the 2002 ICM speaker. He received the Whitehead Prize from the London Mathematical Society and is a fellow of the Royal Society. And I think I probably should stop here, apart from just noting that the title includes analysis, which I haven't mentioned so far, and I look forward to hear.
Yeah, thank you very much for the invitation. Yes, it's great to be here. Right, it is true that the Hodge Conjecture was sort of what got me fascinated with algebraic geometry in the first place, probably true for many of us. Yes, it is, as I say, it's been, this conjecture is 75 years old, so definitely not the oldest of the clay problems, but getting up there. I think it was really bold conjecture at the time, because 1950 was kind of just at the beginning of, it seems to me, of studying really complex manifolds of all dimensions. And to some extent, in the old days, there were algebraic curves and there were algebraic surfaces, and that's where it ended. But this is a sort of bold, in the 1950s, people were beginning to study algebraic geometry in all dimensions, complex manifolds, topology also in all dimensions. And this is a bold speculation, as I hope to get across. And in some sense, it's amazing that such a bold thing could have survived this long, without being knocked down. But then maybe it is true. Yes, and then right, I have to give enormous praise to the Clay Foundation for announcing their prizes in 2000, including this one. It definitely drew a lot more attention to this problem and mathematics in general. Okay. All right. So yes. So one way to, I think it is probably the worst job to try to explain this conjecture to the man on the street. But here we go. So from one point of view, it's about the relation between real geometry and complex geometry. So as we all know, there's a big difference in lots of ways between the behavior of real functions, for example, differentiable or infinitely differentiable functions, the infinity functions, and complex analytic functions. And just as once functions are different, then also in geometric terms, there's a big difference between the behavior of real submanifolds in a real manifold and complex submanifolds in a complex manifold. So some of the differences that we all have heard about are so analytic continuation, meaning that if you have, say in geometric terms, if you have a complex manifold and you would like to sort of perturb it in a small region, well, you're not allowed to do that. There is no, typically, well, let's say in terms of a complex function, say on the complex numbers, if you know, if you have a complex function on holomorphic function on the unit disk, and you know the value on the function on the boundary of the unit disk, the unit circle, then there is a unique way to fill it in. Cauchy's theorem gives a formula for how to fill it in. So complex geometry is rigid in that sense, that you can't sort of change things on a small scale without changing them everywhere. Right. So this is, I mean, my attempt to sort of an attempt at a picture of say the real part of a holomorphic function on the complex numbers. So that's a harmonic function, and it has this property that say the value of that function in the middle of the disk is exactly the average of the function on the boundary of the disk, and it has to be that way. Right. Okay. And so a first approximation of the Hodge conjecture, one could say, is the question in geometric terms: if you're given a real submanifold of a complex manifold, when can you move it in a continuous way until it becomes a complex submanifold? Clearly, you're going to have to move it a lot. There's no way to do this by a small perturbation of a manifold because of this kind of property, things like Cauchy's theorem. If a real function is highly, is much higher at the origin than it is at the unit circle, then you're going to have to change it a lot if it has a chance of ever becoming complex analytic. Okay, right. So I'll sort of gradually get to the more precise setting of the Hodge conjecture. Yeah. So in geometric terms, the sort of nicest example of a compact complex submanifold, compact complex manifold, is complex projective space, which you could describe, as I say, either as points in Cn+1 up to scaling minus the origin, or it has a big open set which is isomorphic to Cn, and then has smaller pieces that are lower dimensional complex vector spaces. Right. So everything is going to be about that and that manifold and its submanifolds, complex submanifolds. Right. Okay. And then yes, as I say here, one other aspect of rigidity of complex geometry is, besides things like analytic continuation, is this Chow's theorem, which says that even though complex analytic functions are very rigid, on a small open set, there are still a lot of holomorphic functions, or in geometric terms, on a small open set in any complex manifold, there's a lot of complex submanifolds. But if you have a complex submanifold of all of this compact manifold CPN, then it's very restrictive. As I say, it has to be defined by, it has to be algebraic in the sense it has to be defined by finitely many polynomial equations. So yeah, if you imagine in C2, you could have the graph of lots and lots of entire functions, but if they're going to close off in a nice way in CP2, in this compact manifold, they have to be just polynomial, given by a polynomial. There's a picture of one particular algebraic curve. I think there's this difficulty in algebraic geometry that the dimensions are sort of too large to draw properly. So this is supposed to represent a complex curve in CP2, which would really be a two-dimensional manifold and a four-dimensional manifold, but it's traditional to just draw the real points. And just remember that we're thinking about complex submanifolds. Okay, right. Let's see. Excuse me. All right. Yeah. So specializing a bit, the setting for the Hodge conjecture is not all complex manifolds, but specifically complex projective varieties, which means well, the smooth ones are those complex submanifolds that you can complex analytically embed into CPN for some n. Maybe n is pretty big. Right, so those are the sort of geometric objects. In some sense, these are the nicest compact complex manifolds. And yeah, the Hodge conjecture just does not generalize in a meaningful way to all compact complex manifolds. Right, okay, and yes, yet another aspect of the rigidity of complex geometry is this fact here that complex submanifolds in CPN or in some submanifold of CPN, they come in only finite dimensional families. That's a little bit vague. Yeah, I want to say that there's sort of a rough analogy with, there certainly is a rough analogy in some ways between things like the Hodge conjecture and things like the Birch-Swinnerton-Dyer conjecture, which let's say is about rational points on an elliptic curve, somehow for an elliptic curve to have a rational point is it's always kind of a miracle. Like maybe at first sight an elliptic curve, maybe it should have the origin, maybe it should have a couple of torsion points, but for it to have sort of other interesting solutions is always a surprising thing. And in the same way, as we'll see more later, complex projective varieties, sometimes they have only sort of the obvious complex submanifolds, but sometimes something special happens and they have more submanifolds than you might expect, more complex submanifolds. Right, so yeah, an example of, well, I guess you can just think, to say this thing about, to justify this idea about finite dimensional families, you can think about the case of complex curves in CP2. So any complex curve in CP2 is given by some, there's these three homogeneous coordinates on CP2, I won't. But anyway, so each complex curve in CP2 is given by some homogeneous polynomial of degree 1 or 2 or 3 or 4, et cetera. And one way to think about what the degree of that equation is telling you is it's telling you the homology class of the complex curve in the homology of CP2. So a complex submanifold or even a real submanifold determines a homology class in CP2. CP2 is a 4-manifold. This is living in the second homology because it's a real 2-dimensional submanifold. And that homology group is just the integers. So basically the degree of this equation tells you the homology class of your complex submanifold. And so if you think of that backwards, if I'm given a complex submanifold of some known homology class, then there's only a finite dimensional family of such complex submanifolds because there's only given the degree, there's only a finite number of coefficients this polynomial can have. Okay. Yes, I guess I'm sort of saying some of that here. Right. So in topological terms, yes, if you're given, I think these are closed-oriented manifolds. If you're given a real submanifold, of codimension B, I'll use that codimension notation. So it has dimension B less than the dimension of a whole manifold. Then it gives you an element of a certain homology group, which I prefer to view as this cohomology group. So anyway, H upper B is some group in which codimension B submanifolds have a class. Right. And then, as I say, a next approximation of Hodge conjecture is the question, if you're given a smooth complex projective variety, then which elements in the cohomology can be represented by not just real submanifolds, but complex submanifolds? Right, so of course that has to be about, you could only ask the question for even degree cohomology because a complex submanifold is even real dimension, or even real codimension. Okay. Right, so Hodge proposed an answer to that question, or sorry, to a version of that question. There are a few details to fix up here. Right, okay, so Hodge's, in some sense, Hodge's main theorem, perhaps from the 1930s, was the Hodge decomposition theorem, which says that smooth complex projective varieties, well, they are real manifolds, so they have cohomology like any real manifold or topological space does, but because they're also complex manifolds, they have a certain extra structure, this decomposition of the cohomology, which really depends on the complex structure of X. So we'll see more of this later, but if you change the complex structure on X while keeping the same real manifold, you actually do change this decomposition, as we'll see. Right. But anyway, so the way it looks is on the cohomology in any given degree. Maybe cohomology is defined with integer coefficients, but if you tensor it with C, you get a complex vector space, and that complex vector space, decomposes as a direct sum of certain complex linear subspaces that have some geometric interpretation of their own, as I say here. You could ignore it if you like, but they are sheaf cohomology of X with coefficients in the sheaf of holomorphic forms of different degrees. Okay, right. So yes, I'm writing here a few words about the proof of the Hodge decomposition. I mean, this is kind of an interesting thing in the sense that Hodge had this, well, yeah, this brilliant insight, I guess, that the cohomology of these complex manifolds should decompose that way. Probably he really didn't prove it in the 1930s. In some sense, he was inspired by Maxwell's equations in physics, and he sort of brilliantly realized that you could generalize Maxwell's equations in terms of differential forms on a manifold of any dimension. Basically, you could view those equations as saying that some 2 form is harmonic, and he defined what harmonic should mean for differential forms on any manifold. Yes, but then to justify the things he wanted, like that decomposition, you really need hard analysis. You really need some theory of linear elliptic PDEs, which is maybe the nicest part of PDE theory, but on manifolds, and that really had not been developed in the 30s. So maybe this was finally justified around 1950 by Kodaira and others. But anyway, the plan of the decomposition theorem is, right, so look at this again. Right, so there's different ways of thinking about cohomology, but when you think about cohomology with real or complex coefficients, you can think of it in terms of differential forms, and that's inherent in this. I mean, that's sort of where this theorem begins. Okay, so you can think of, for any real manifold, you can interpret cohomology, say, with complex coefficients in terms of differential forms, say, tensored with the complex numbers. But if, in particular, X is a complex manifold, then you can pick out special types of differential forms, as I say here, because they're special. I mean, differential forms are basically D of functions, and there's different special types of functions on a complex manifold. Namely, there's holomorphic functions, those ZIs there, and there's also anti-holomorphic functions, the conjugates of holomorphic functions. And if you basically look at differential forms that involve a certain number of holomorphic parts and a certain number of anti-holomorphic parts, that's called a differential form of type J comma A minus J in this case. And basically that is the source of this decomposition. So you you interpret all the cohomology in terms of A forms, differential forms of degree A, and you want to decompose those A forms into those of type J and A minus J. Unfortunately, that decomposition doesn't fit well with the differential, so it's not obvious that that gives a decomposition of the cohomology, and so you need to do some hard analysis to represent the differential forms, I mean, by especially nice ones, harmonic forms. Basically, the idea would be think about all the forms that represent a given cohomology class and look at the one with the smallest L2 norm. We have to show that such a thing exists and is unique, and it does, but anyway, but that ends up implying this decomposition. Okay, right. So yes, so sort of heading onward towards the Hodge conjecture. Hodge made the following. So you have that decomposition of all the cohomology of a complex projective variety. There are somehow, especially interesting cohomology classes, which is the classes of complex submanifolds or subvarieties. I use the word subvariety for something like a submanifold, but it could have singularities. That still defines a cohomology class. So anyway, the fact is that a complex subvariety determines not just any cohomology class, but it always lies in the middle of the Hodge decomposition, in this HAA part of H2A, if we're talking about a complex subvariety of codimension A. Yes, and again, I will say a few words about why this is, perhaps unwisely, but it's somehow, it is a, there's a nice reason for that. Why do complex subvarieties live in the middle of the Hodge decomposition? So I look at the special case for this, just to give an idea, take the case of a complex projective surface. So it has a complex dimension 2, real dimension 4, and consider a complex curve in there, so real dimension 2. And I would like to show that, the Hodge, so Y determines an element in this H2 of the manifold X. H2 decomposes into these 3 parts. And we want to show the cohomology class of a complex subvariety lives in the middle piece. So as I said, these parts have particular interpretations, and in particular, one of them is H0 of omega 2. In sheaf theory language, H0 means the space of sections of a sheaf. So that's the space of the complex vector space of holomorphic 2 forms, which is finite dimensional. Maybe not obviously. Okay, and so I guess another maybe just detail of this proof is that the way complex conjugation. So you could talk about complex conjugation on the complex coefficients there, and the effect that has in terms of this decomposition is that it switches the left and right sides. And a complex subvariety, it determines an integral cohomology class, in particular a real cohomology class. So whatever the class of y is, it's going to have, if it's non-zero on the left piece, if it's decomposition on the left piece is non-zero, then the decomposition on the right piece is non-zero too, and vice versa. So basically, because of that, all you need to show is that the cohomology class of y, if you project it to either the left or the right piece, you want to show that you get 0. But if you think of what maybe projecting to the right piece means, that is literally, you have to show that the pairing, the intersection pairing of a holomorphic 2 form, which gives you a cohomology class, with the class of this complex curve gives you 0. I mean, so I want to show that the pieces of this cohomology class on the left and right are 0. But why is that? Because it turns out this pairing is given just by integrating a holomorphic 2 form over this algebraic, this complex curve. And the point is, when you restrict a holomorphic 2 form to a complex 1 manifold, you just get 0. On a complex manifold of dimension n, you have holomorphic forms of degree up to n, but nothing beyond that. So because y is a complex curve, this just has to be 0. Okay, sorry. Right, so I will, sort of state the Hodge conjecture finally and precisely. So it's about this situation. So you have a smooth complex projective variety, that is a complex submanifold of CPN for some big N. And then the question is about sort of what complex subspaces there are of X. So the conjecture is that every rational cohomology class that lives in the middle of the Hodge decomposition must be essentially algebraic. That's to say, to be precise, it's a finite linear combination with rational coefficients of some complex subvarieties of codimension A in X. And such a linear combination is called an algebraic cycle. So basically, you might wish to characterize like exactly which cohomology classes are literally the class of A complex subvariety, but that's too hard. And in any case, there's no such general description of that. So you have to allow like differences, maybe one subvariety minus another subvariety. Then you can at least hope for this characterization. Yes, okay. And there are sort of many details. The statement has been kind of fought over. Hodge originally made a statement which was stronger in 2 different ways, and both of those statements turn out to be wrong. But this is sort of what's left, what may actually be true. In particular, Hodge originally made a version with integral cohomology, which might look nicer. But again, the integral Hodge conjecture turns out not to be true in general. As it turns out, like in many talks in this week's conference, it is very interesting to ask when the integral, for which varieties the integral Hodge conjecture is true. And it says a lot when that's true and when that's not true about the geometry of variety. But I'll focus on this rational version. Okay, a key remark, which I will say more about in a couple of slides, is that, this is really about the interaction between 2 different types of structures. It has to do with the interaction between the rational cohomology and the way that differential forms decompose. And they're really, they're somewhat orthogonal kinds of things. In particular, the Hodge decomposition, as I wrote here, is only decomposition of the complex cohomology. It does not come from any decomposition of the rational cohomology. And so that intersection is a rather subtle thing, as we'll see. Okay, in the next couple of slides, I talked about what is perhaps the first non-trivial case of the Hodge conjecture. Namely, you take your complex manifold to be a smooth surface defined by a polynomial of degree 4 in CP3. Such a thing is called a K3 surface, famously. So there's a particular example of a K3 surface defined by that particular polynomial equation. But it's crucial to realize that there's lots and lots of, there's a continuous family, of course, of polynomials of degree 4 in those variables. And as you vary the coefficients, you typically change the complex manifold that you have. So they're all going to be diffeomorphic as real manifolds. There's only one K3 surface as a real manifold, but as complex manifolds, there's this continuous family of different ones. And they have interestingly different features. I think this is the picture is one particular quartic surface. As usual, we throw a real picture and pretend it's the complex picture. Okay. Right. Right. Oh yes. So maybe I should say so why do I start with surfaces of degree 4? So the reason is just that surfaces of lower degree, quadratic surfaces or cubic surfaces, their cohomology is kind of trivial from the point of view of the Hodge decomposition. Namely, all the cohomology is in the middle piece, the Hodge decomposition. All the cohomology, I mean, the Hodge conjecture is true in those cases. All the cohomology is algebraic. For example, a cubic surface famously has 27 lines, and that is to say CP1s contained inside it. And those lines span all the cohomology, so the Hodge conjecture is true, but not so exciting. Whereas in this case, degree 4, not all the cohomology is algebraic, and it's a more interesting challenge to see does the part of it which Hodge predicted to be algebraic, is it actually algebraic? Okay, right. So yeah, here I write out what the Hodge decomposition looks like in the case of K3 surfaces. So the second cohomology with integer coefficients is an abelian group of rank 22. Therefore, the cohomology with complex coefficients is a complex vector space of dimension 22. And the Hodge decomposition looks like this. So you have a 1-dimensional, 20-dimensional, and 1-dimensional piece in this decomposition. Right, okay, and yeah, this is sort of a crucial point to realize about the Hodge conjecture. So imagine this family of quartic surfaces as the coefficients of the polynomial vary. If you imagine varying the coefficients just a little bit, you can think of the integral cohomology of these. So this is supposed to be a picture of the integral cohomology of these K3 surfaces. So it's an abelian group of rank 22. You could imagine that as being just like a fixed abelian group, because sort of topologically all of these K3 surfaces are the same. But the way the decomposition works, that's a decomposition sort of inside like this vector space, this abelian group tensored with C. Again, what I'm sort of drawing is more like that abelian group tensored with R. But anyway, but yeah, in this cohomology tensored with C, you have this decomposition. Imagine, I guess the green line is supposed to represent H11. There would be also a part that represents H02 and H20. But the point is that as you vary the coefficients of your equation, vary your K3 surface, then these complex subspaces move in a continuous way. And right, in particular, sort of, so they're not sort of neatly lined up with this, with the integral structure in this cohomology in general. And therefore, the intersection that comes up in the Hodge conjecture, that is H11 intersected with the integral or rational cohomology, that can have different ranks depending on which K3 surface you have. That's what I say here. So for different quartic surfaces, what's called the group of Hodge cycles, there's this intersection, integral cohomology with the H11 part. It's an intersection inside the complex cohomology. Well, it's going to be a finally generated abelian group, right? Because it's contained in Z22. But the rank will change as you vary the coefficients. So if you imagine what's, like how much does a complex vector space intersect a lattice, typically the intersection is going to be kind of small. So what happens is that for most quartic surfaces, this intersection has rank 1. But then in special cases, there will be sort of more of an overlap than usual, the H11 with the integral cohomology, and then this rank B will jump up. The group of Hodge cycles will have higher rank. And so that sort of indicates like what the Hodge conjecture says in a philosophical sense. Like it's sort of telling us, or it's predicting that somehow like most quartic surfaces or any other, this would apply to kind of any family of algebraic varieties, most of them don't have many interesting complex submanifolds, only the obvious complex submanifold, so to speak. But then somehow special varieties in the family will have sort of unexpected complex subvarieties. And the neat thing is that according to the Hodge conjecture, that how much that happens is predicted by this kind of linear algebra of how this integral lattice intersects this complex subspace. Yeah, as I say here, I mean, one could sort of say much more about this, but this has to do with what we don't understand about calculus. So how would I put this? Like if you want to know, like if you want to say compute how big the rank of that intersection is, it's not easy because it basically has to do with the question of like, is the slope of this H11 subspace in terms of this integral cohomology, is it rational or irrational? Or really, because it's higher dimensional, sort of how much is rational and how much is irrational. It's not easy to tell whether a given number is rational or irrational. If you think about like how these numbers actually rise, they're literally given by integrating certain differential forms over certain submanifolds. And basically, in calculus, we have the feeling, we sort of give our students the impression that we know how to integrate. But that's really not true. So some functions we can integrate explicitly, but of course some functions, even algebraic functions, even if you want to integrate an algebraic function over a fixed region, sometimes you just get transcendental numbers. And if you want to know, is this integral rational or irrational? Well, we don't know in general. That is the same issue that arises in trying to understand this group of Hodge cycles. So basically, the Hodge conjecture, I guess you could say, is predicting that integrals should be irrational unless there's a geometric reason for them to be rational, which maybe makes sense. Okay. Right. So I will maybe briefly mention. Yeah, I think I. So the main case of the Hodge conjecture, which is true, is that it is true. For example, in the case of quartic surfaces that I just mentioned, because more generally, it's true for codimension 1 algebraic cycles. So yeah, so for any complex projective variety, if you have an element in H upper 2 with integer coefficients that lies in the correct part of the Hodge decomposition, then it actually is algebraic. The proof of that is interesting. I don't have time to say it, but let me do this anyway. So the proof uses the crucial point maybe in all this is that, or in some sense the reason we can prove the Hodge conjecture in that case and not in others is that we kind of have a geometric interpretation for, say, cohomology in degree 2 and not so much in higher degrees, or not in the same way. So, codimension 1 algebraic cycle, looking for codimension 1 algebraic cycles turns out to be the same thing as looking for holomorphic line bundles. Line bundles have to do with the group C star, and you can analyze the group C star using the exponential function, which basically allows you to sort of, the way this proof works is you can sort of relate line bundles to kind of more additive invariants that have to do with Hodge theory because of that C in the middle there. And in some sense, yeah, I mean, part of the issue for the Hodge conjecture in general is that we would really need some sort of satisfying geometric analog of line bundles in higher dimension, and vector bundles are just not quite the same thing, not as good. Yeah, let's see. Right. Okay. So going through this quickly, the Hodge conjecture, the sort of other known case of the Hodge conjecture, which follows from that case of codimension 1 cycles, is by something like Poincare duality. That's a little misleading. Really, this another theorem of Lefschetz is the hard Lefschetz theorem. Because it's true for codimension 1 cycles, one can argue that it's also true for one-dimensional cycles. Okay, let me just skip any details. But then, so that means that the first open case of the Hodge conjecture, which has remained open since 1950, is for two-dimensional algebraic cycles on a four-dimensional algebraic variety. And that really seems hopelessly difficult. Yes, let me skip this. So, yeah, so some of the people who basically, like all of algebraic geometry since that time has been inspired by, struggling with the Hodge conjecture. In particular, I wrote Griffiths and Deligne as people who developed a theory of variations of Hodge structure. This result by Catani, Deligne, Kaplan is a sort of, crucial piece of evidence for the Hodge conjecture that wasn't obvious at the beginning. So, so basically, the Hodge conjecture would predict, yeah, it's about this situation of when you have a family of algebraic varieties, you can ask sort of two questions, like which are the varieties where there's extra algebraic subvarieties, and which are the varieties for which there are extra Hodge classes. The Hodge conjecture predicts that those should have the same answer. So an interesting point is that the subset where there are extra algebraic classes kind of must be algebraic, an algebraic subvariety, whereas the subset of Hodge classes on the face of it is only a complex analytic subspace. But in fact, these authors showed that the set of, the locus where there are extra Hodge classes is actually algebraic, to put it briefly. Really, it's a countable union of algebraic subvarieties. But nonetheless, that really wasn't obvious at the beginning. And so it's one of these ways in which the Hodge conjecture it definitely has the feeling that it's pointing you in the right direction. You know, there's more reason to think that it's true now than in the past. So I was supposed to talk about developments since 2000, and you know, Claire Bazin is sort of has made enormous contributions during that time. She's at this conference. I just picked out a few of many things. So, for example, the Hodge conjecture would make, on the face of it, perfect sense for compact Kähler manifolds, not just complex projective varieties, which are a special case, but basically she disproved it in any reasonable form, which is somewhat disturbing. If you imagine trying to attack the Hodge conjecture using analysis, you might imagine that your proof would work for compact Kähler manifolds, but it can't work. Yeah, and as I say, she's done an enormous amount to understand the integral Hodge conjecture, sort of when it's true, when it's not true, and what it means about other questions like rationality when it's not true. Okay, so I'm leading up to a certain conclusion, which is the sort of you know, a big advance on the Hodge conjecture by I.L. Markman, who's also here in the past year, and that suggests a certain line through history. So Spencer Bloch made you know, enormous contributions to algebraic cycles from different points of view, but I want to focus on one of his ideas, which is about, okay, this basic situation that I've been talking about. So when you have a family of smooth complex projective varieties, yeah, let's say that maybe on one particular variety in this family, you have an interesting kind of non-obvious complex subvariety. Perhaps you're in a situation where the Hodge conjecture would predict that that should extend to a family of algebraic subvarieties in the whole family. And I guess, yeah, Bloch observed that in some sense, like a large part of this problem, something that's called the variational Hodge conjecture, it seems to be a question about the difference between solving a problem kind of at a formal power series level and solving it globally. Yeah, so he proved a theorem called semi-regularity theorem about saying that sort of in a certain special case, if you make enough assumptions, then if you can solve this problem infinitesimally locally, then you can solve it globally. The problem is that this assumption of semi-regularity seems absurdly strong, and it's hard to find, you know, any interesting examples where it is valid. But nonetheless, this is an important point of view, which I will. So okay, there's the following horrible slide. Let me just say, so let's see. There is the following definition. So just forgive me. On a complex projective variety, given a coherent sheaf, so a coherent sheaf is, it could be an algebraic vector bundle. In general, it's something like the co-kernel of a map between two algebraic vector bundles. So it's like another way to encode algebraic subvarieties of X. Okay, in that situation, you can define a certain cohomology class called the Atiyah class of E. That arose in Atiyah's work basically as a way to give a definition of the Chern character or Chern classes of E, if you imagine E as a bundle. So anyway, what do I want to say? So by taking sort of powers of the Atiyah class, taking a certain trace, you get a map from this again, this weird cohomology group, second X group between E and itself, and some pieces of the Hodge decomposition. Right. So yes. Okay. So what do I want to say? So why consider, you know, let's see, this, yes. Okay, so this notion of semi-regularity is saying that this map here that you can define is injective. And basically, this is a property that a coherent sheaf might or might not have. Yeah, maybe it's not clear why you would ever consider this or why it would ever be true. But let me try to explain. So the idea is that what this map is about is the following question. So imagine that you perturb your complex manifold X. Then you may ask, does this coherent sheaf extend to first order as you change X? That may or may not be true, but the obstruction to that being true lives in this group here. Okay, and then there's another question you could ask, which is, well, if that's going to be true, if this coherent sheaf can be perturbed, then at least the Chern classes of E have to be perturbed, and they have to remain Hodge classes, because Chern classes of a coherent sheaf are algebraic, and so if you could perturb E, you would have to be able to perturb the Chern character of E as a Hodge class. And it turns out that this injectivity precisely says that, well, basically, if you can perturb the Chern classes of E and keep them Hodge classes, then you can really perturb E geometrically, which is sort of what you want to do for the purpose of the Hodge conjecture. Okay, let me do this. Right, okay, and so, yeah, so that's, semi-regularity is sort of saying that this coherent sheaf kind of, its infinitesimal deformation theory is well covered by it's well related to its to whether its Chern classes deform as Hodge classes. But in fact, there's a theorem extending what Bloch showed that basically says, if you have a family of smooth complex projective varieties, and if you have a coherent sheaf on one of the varieties in this family, and if by magic it's semi-regular, right? Suppose that the Chern classes of this E can be extended to rational cohomology classes in the whole family. That's a kind of condition about these classes being preserved by the monodromy of this family. If that's the case, then so under all those assumptions, this coherent sheaf extends to a coherent sheaf on every variety in the family. Yeah, and in particular, it follows that the Chern classes of E remain algebraic everywhere in the family. This is sort of miraculously strong, I should say, because I didn't even assume in this statement that the Chern classes of E remain algebraic, remain Hodge classes. So this seems like sort of more than the Hodge conjecture even. The point is, though, that one of Delen's great results is that exactly this, that if you have a Hodge class at one fiber, which is sort of preserved by the monodromy of some algebraic family, then it is automatically a Hodge class everywhere in the family. And so, yeah. So there is a reason to expect these classes to remain algebraic, and actually, under these crazy assumptions, they do remain algebraic. Okay, right. So the last thing I will talk about, which sort of motivates why I did that last step, is Markman's theorem in the past year that the Hodge conjecture is true for abelian varieties of dimension 4 and 5. So abelian varieties are compact complex tori. That's the best picture I could draw. Yeah, so topologically, it's just S the circle to the 8th power or the 10th power. But the point is that it's not just a real manifold; it's a complex manifold. There's a whole continuous family of different complex manifolds with this that are topologically torus, and these are very, very interesting complex manifolds. Also in number theory. And for all the varieties in this family, the Hodge conjecture is true. So let me just go on. Some of the background for Markman's work, I would say it's clear looking at his papers, several papers over the past year. It's clear that some of the motivation comes from big theories which have been developed in algebraic geometry. One is the theory of hyperkähler manifolds, which has nothing apparent to do with what I've been saying, but it definitely did influence this whole line of thought. Hyperkähler manifolds are the manifolds, say, with that are sort of even nicer. You could say like the quaternionic version of algebraic varieties, perhaps. Holomorphic symplectic varieties would be another word for it. Anyway, somehow those varieties, it turns out, can be studied in enormous depth and detail, and in particular things like when do you have if you have a vector bundle on one hyperkähler manifold, when can you extend it to a vector bundle on the whole family of hyperkähler manifolds? That kind of thing can be studied extremely well, and it definitely led to these ideas here. Another theory is the theory of not just algebraic vector bundles, not just coherent sheaves, but complexes of coherent sheaves, which again has been developed a lot and sort of goes into these proofs. Okay, so just I'd like to sort of describe the ideas in Markman's proof as well as I can in a few minutes. Right, so the idea is, let's say, take the case of abelian fourfolds. Of course, abelian fivefolds with similar ideas. Yeah, so right. So the idea is that the Hodge conjecture is known for codimension 1 cycles and for one-dimensional cycles. So the only issue is about 2 cycles. That is, you take a rational cohomology class in degree 4, suppose that it's a Hodge class, and then, in other words, that it's in the middle piece of the Hodge decomposition. And then you want to show that it can be represented by some rational linear combination of algebraic surfaces contained in this abelian variety. So yeah, a thing to realize is that if you imagine the family of all abelian fourfolds, for most of the varieties in the family, this is completely obvious because for most of them, that intersection, the group of Hodge cycles, will be very small. We'll just have rank 1. And so you just need to write down one algebraic surface in X, which is easy. X is always embedded in some big projective space and just intersected with a linear space that will give you some algebraic surface in X. So yeah. So this is the thing where it's sort of obvious for most abelian varieties. The interesting thing is it true for all, even the more special abelian varieties? So Andre Weil analyzed the possible special Hodge structures on the abelian fourfold can have, and turns out that the interesting one are what are called abelian varieties of Weil type, which in short, these are not the most special ones, not so-called complex multiplication ones, but they're somewhat special in that they have this endomorphism ring tensor with the rationals containing an imaginary quadratic field. Right, so what Weil discovered is that, so I guess there's a 10-dimensional family of all abelian fourfolds. There's a 4-dimensional family, subfamily of abelian varieties of Weil type. And for most of the abelian varieties of Weil type, the group of Hodge classes has rational vector space that has dimension 3. There's sort of this obvious class on the left, a linear space section, and then there's this other class called the Weil Hodge classes, which is, anyway, what do I want to say? I think you can define it directly in terms of linear algebra, let's just say. Okay, not say more. So Markman's basic approach is to use the semi-regularity theorem. I almost feel like this may be the first time this theorem has been used in a serious way. Maybe I'm saying that too strongly. So yeah, the idea is that he just starts with one very special abelian fourfold of, I'm sorry, right. So the issue is, it's known that to prove the Hodge conjecture for all abelian fourfolds, it's enough to prove it for the ones of Weil type, and specifically to show that these so-called Weil Hodge classes, the ones in that space on the right, you want to show that those are algebraic. We certainly don't know like any obvious geometric construction of a surface in X that would represent that. Except maybe in special cases, in some sort of very, very special abelian variety of Weil type, maybe you can just sort of write down the surface by hand that does the trick. Maybe I should say this. Yeah, okay. And then, the plan would be, so these Weil classes, they remain Hodge classes definitely on the whole family of all abelian varieties of Weil type. So they're kind of a monodromy invariant class, a bunch of cohomology classes. So yeah, you would kind of be done by the semi-regularity theorem if you could arrange that on one abelian variety of Weil type, you could represent these Hodge classes as Chern classes of some semi-regular coherent sheaf. You just have this one, it's showing that this one, you have to show that this arrange that this one weird linear map that I wrote is injective. It just seems like insanely difficult to do that. But Markman succeeded, and I guess some of the tricks that came along were that there's sort of different, there's sort of countably many discrete invariants that abelian varieties of Weil type has. In order to deal with all of them, he actually reduced the argument to showing that a certain special class of abelian varieties of dimension 6, also of Weil type, that their Hodge classes are algebraic. And let's see, yes. And in some sense, right, even at the end, even in this, the nicest possible abelian surface that he looked at, he couldn't actually find, in some sense, literally a semi-regular coherent sheaf. He needed a generalization of the semi-regularity theorem where you consider what are so-called twisted sheaves instead of sheaves. It's like a coherent sheaf on an algebraic stack, if you want, related to your variety. But anyway, so, oh yeah, and then I just mentioned that the very special abelian sixfold of Weil type that kind of gets the argument started off is this very simple thing. You take a curve of genus 3, you take its Jacobian, which is an abelian variety of dimension 3, take the product of that with itself or its dual abelian variety. And sort of there, because you have this special geometric feature, this curve sitting inside this abelian threefold, you can mess around with that. You can do things like translate that curve using a finite group of translations and take the ideal sheaf of that curve. So there's quite a lot of trickery, messing around, applying automorphisms of the derived category before finally Markman finds a coherent sheaf that satisfies the semi-regularity assumption. So I guess I would conclude by saying that this proof, I mean, it's complicated, but in some sense there's a lot of hope in the fact that it's complicated, because now you can try to look for look for other complicated constructions like that. There's a lot of hope in proving the Hodge conjecture for other important families of varieties. So I guess semi-regularity, seemed like too rare a thing to ever be used effectively, but basically Markman developed a bunch of tricks, things like using a finite group and looking for equivariant coherent sheaves with respect to that finite group. There's a bunch of tricks that now you can hope to use that to arrange for something like semi-regularity, and thereby reduce the Hodge conjecture for some whole family of varieties to one special case. Okay, thank you.